Ça a l'air de... Record. Ok. Record. Ok, c'est parti.
C'est bon si je fais ça, on voit pas vraiment. C'est jamais.
Okay, good morning everyone. Welcome back. Today's the fourth lecture and I will be talking about cosmic inflation. And the reason it is relevant to the entire picture is that cosmic inflation solves a number of problems in cosmology. And its most important use today is the way it seeds the structure formation. It gives rise to the initial density perturbations when the structures grow. I will talk about the connection of today's story to the previous lectures, and I will introduce the problems that inflation solves, and I will explain how inflation generates perturbations. And today I will not talk about CMB polarization, even though I initially thought I would, but I think I will fill the entire time with talking about inflation. Polarization then is postponed until the next lecture because we have one more to go. So I think that is a safe choice. So what did I mention in the previous lectures that is relevant today? It's a story of correlations. Structure in the universe has a power spectrum. You take a Fourier transform of the map that you get. And in the case that this structure arises from a Gaussian random density field, a Gaussian correlated density field, then the Fourier transform of this single realization of the density field that we have probes the distribution function of the initial conditions. It's not a measurement of the distribution function, but it is a quantity that is closely related to it, and it does depend heavily on the initial distribution function. So for the cosmic microwave background, the distribution function is given by the multiple moments CL, and the Fourier transform of the map gives you the pseudo CLs, or in our notation the DL, multiple moments, which for large L are a very good measurement of the CL. Large scale structure is a three-dimensional observation, or actually it is not entirely the case, but you can transform it into a three-dimensional spatial map, take the Fourier transform, and then you have a handle on the distribution in Fourier space of the same density field. But what we did not discuss so far is the generation of the initial conditions from which these two functions grow through the gravitational potential. I've shown you the differential equation that gives you the time evolution of the gravitational potential, and I have not given you the initial conditions. For example, it could be that this potential starts from a completely random distribution without any correlations. The time evolution that I've shown so far then still holds, it still works. But the question is, what is the initial condition and is it correlated or not? So, what would be the case, what would happen if the potential had initial conditions that were completely uncorrelated? I first want to show you that and show you what the universe would look like then, and convince you that this is not the solution. So to remind you, a two-point correlation function of a white noise, with white noise, is a delta function. So there's only the autocorrelation at equal positions x, but the function at two different points x is not correlated. So if I had an infinite number of universes, I pick my point x, which is for example here on Earth, and I take another point y, which is for example a million light years away, and I multiply the densities and average that over all infinite new cosmologies that I have access to, I will find 0, because they're uncorrelated. Of course, one individual realization, I have a density here, I have a density there, the answer will be non-zero. But the average of infinitely many cosmologies will be 0 if they're uncorrelated. Now, if it's white noise, that is saying that the autocorrelation of these random variables has the same variance everywhere. That is just a special case of white noise. It is uncorrelated, but you have the same variance everywhere. Now, if you have white noise, we can continue and look what that means for the power spectrum. The autocorrelation function can be transformed into Fourier space. There's this from here to here it's an identity, there's nothing about white noise. But if the Fourier transform of the two-point correlation function has to be equal to this delta function, then you can see straightforwardly that this correlator in Fourier space must again be a delta function times the constant sigma squared. Only that way you get this quantity out of this integral. That is as much as saying that the power spectrum must be a constant. But then the question is, so if I have white noise, everything is uncorrelated with one constant variance for all the autocorrelation functions. But the question is, it is white noise in what? Which is the quantity that is uncorrelated? Because if one quantity is uncorrelated, the other one may become correlated. Look, for example, at the Poisson equation. The gravitational potential is related through its second spatial derivative to the density perturbations. So, the power spectrum of the potential, if you go to Fourier space here, you get a k squared, so the power spectrum, which depends on phi squared, is different by a factor of k to the fourth. I think this should be a minus 4, I made a typo there. Yes, this should be a minus 4. So P, the power spectrum of phi and the power spectrum of density perturbations differ by a factor k to the fourth. So, if the density perturbations have white noise, and their power spectrum is a constant, here we have a sigma, then the perturbations in the gravitational potential will be similar, but with a factor k to the fourth here. So then the power spectrum will not be constant. So actually in the gravitational potential then, I will measure two-point correlation functions. Okay, because they're related through derivatives or integrals. It's a non-local relation. So even if you measure a p of k, which has some form of k to the power n, you're still not entirely sure that the origin of the system may be uncorrelated. But you do know that the quantity that you are measuring depends on more positions in space-time than just its autocorrelation. Because if you take the derivative, you need to know of neighboring points. Okay. So, what does it look like in the universe? Here is the power spectrum of density perturbations. We've seen that in previous lectures as a function of wave number k. So remember that large k corresponds to small scales, small k corresponds to large scales. The blue dotted line is the best fit matter power spectrum to observations. So observations prefer this distribution of density perturbations. If we choose a power spectrum that has no two-point correlation in the density functions at the initial conditions, and we evolve that in time using the differential equation that we discussed, you get the red line. So you see that on very large scales, the absence of a two-point correlation is preserved. On small scales, the potential does evolve in time because of gravity. So you do get a scale dependence of the power spectrum, and you do get some correlations. But clearly the shape of the blue line and the red line do not correspond. So the density perturbations are correlated in the universe, and the question is, what gave these correlations? Now, before I say anything about inflation, I want to talk about something that is older than inflation, and that is an argument which tells us what the power spectrum should look like if you want the universe that looks like our universe, even without considering accurate measurements of galaxy distributions and without considering accurate measurements of the C and D correlation spectra, which is an argument independently by Harrison and Zeldovich, and in fact also by Peebles. It starts with realizing that in an expanding universe you have a horizon. That is, light can travel at most a distance that is dictated by the age of the universe. Straightforward. Light is a constant velocity, so if the universe is 100,000 years old, light can only have traveled 100,000 light years. So 2 points that are more than 100,000 light years apart will not know about each other at the time of 100,000 years. They will have never been in contact with each other. That's the horizon in an expanding universe. The question that Harrison and Zeldovich asked is, what is the amplitude of the autocorrelation in density perturbations in Fourier space for a mode with a wave number, with a wavelength that corresponds to the horizon size. That is, given all the matter that we have access to in our past light cone, what is the amplitude of density perturbations that goes inside this scale? Now, the next step is to assume that we do not live in a preferred epoch in the history of the universe. We don't live in a special time. Otherwise, if you assume that we live in a special time, then actually you could take anything and design a universe that happens to accidentally look the way it does right now, right here, but will look wildly different tomorrow. And that's a possibility, but that's a model with many parameters. So if you assume that we don't live in a special place, then the dependence on time of these different perturbations will scale as a power law in t. That is, the horizon, the size of the horizon, scales with t. So actually at each different time, this question concerns a different wave mode. Right? Early time, small horizon, we're talking about a wavelength of the small horizon size. At later time, larger horizon, we're talking about a different wavelength in the density field with a different size. And the question is, what is the amplitude of that perturbation at each time, the perturbation that corresponds to the horizon size? It must scale as a power law in time, otherwise there is a preferred epoch. And if that is the case, you can straightforwardly see that if n is less than 0, the power law in t, then in the past there will be a divergence in the density perturbations. When the horizon is very small, you will have very large perturbations if it scales as t to the power n, without considering the physics that gives rise to it. But simply from the fact that you have a divergence in the past, if n is less than 0, you must conclude that the local universe must have already collapsed to a black hole, because you will, at some time in the past, certainly reach densities that are so large that the matter is inside its own Schwarzschild radius. So you will have collapsed to a black hole. And this goes for every point, for every single point inside a horizon. So for every region inside the horizon. So every part of the universe would be part of a black hole, if this is the case. Similarly, if n is larger than 0, in the future there will be a divergence. So we could live in a universe that looks like that right now, and in the future it will certainly collapse to a black hole. That also means that we live in a special time. So the universe is not a black hole yet, but we're just lucky enough to live right now before the universe becomes a black hole. So the conclusion from this line of reasoning is that there's only a non-special time if this power n is 0, which means that the density perturbations at the wavelength that corresponds to the horizon size always have the same amplitude. So at an early time, small horizon, I have an amplitude that's equal to, let's call it 1. At a later time, later horizon, the density perturbation that corresponds to that size also has an amplitude of 1. Only if that is the case, the universe is not one big black hole in the past or in the future. This is the argument for the Harrison-Saldovich spectrum. And this translates if you actually compute the power spectrum, which in this case gives you the power per using integral dk over k. Therefore you get a different power of k in here. This translates into a power spectrum p of k that is proportional to k.
But what is the problem with this thing that we live in a special time, if you wish?
And that is a good question, because now that I say it, I realize that actually with the cosmological constant, that is exactly what is happening.
Exactly.
We live in a different type of very special time, and we're accepting it. And somehow for the density perturbations in the past we did not accept it, but then the cosmological constant also was not there. So that was a valid question. So yeah, you could say that actually this argument for the future, yeah, it's an extrapolation. You don't know the future, so if you want to say anything about the future, you're extrapolating something, and there's a...
Yeah, because we do live, as you say, I mean, you see it as the cosmological constant, but if you look at the different types of matter, so to speak,
yeah,
I mean, they don't differ by orders of magnitude as they were, for example, in the past.
Mm-hmm.
So in that point of view, we do live in a special...
Yeah. Yeah, exactly.
It could be interpreted as we We live in a special universe.
Yeah.
So,
No, exactly. So,
so the one with the n negative, I mean, I take it because we are here, in a way.
Yeah. So the first argument is stronger because this says that we would have been in the black hole already. And
Yeah, and then that's, you know.
So this is actually a measurement. The second one is an extrapolation and not an observation. Yeah. So that's more taste than science. Yeah, that's true. So the argument is not so strong for the upper bound.
It's the same kind of idea according to which the vacuum has to be stable.
Absolutely.
If you are only marginally stable, or if you have an n which is kind of small but still positive,
Yeah.
we could live long enough to see it.
To see it happen. In fact, you lose its constellation point there. Indeed.
But see, sometimes particle physicists are accused of being, you know, holding too much to this naturalness problem, and you know, and then, cosmologists and astrophysicists don't have that problem, you know.
I really
Things
think
happen, you know, like for example the fact that the moon is where it is,
Yeah.
you know, the distance to the Earth. Otherwise, we wouldn't have had, you know, the lemma, tides, you know,
Tides.
all kinds of stuff, you know. So, oh, well, they don't care about that.
Right.
But now you come and you say, well, look.
What I find more interesting about the moon is that it has exactly the same angular size as the sun.
Yeah, okay, but is that natural?
It was, remind me who invented the entropy principle?
Never mind.
Particle physicist, right?
Never mind, okay.
But he was trying to do cosmology, right? So, Harrison and Zalovich and Peebles came through a simple reasoning that the past universe cannot be a black hole, and the future universe preferably is not a black hole. Came to a power spectrum that actually is this magenta line. I hope you can distinguish it from the blue line at your distance where you're sitting. So if there were no two-port correlations, we would have the red spectrum, but this would mean that at some point the universe becomes a black hole. By the arguments of Harrison and Zalovich, we get a spectrum that has a scale factor of, sorry, that has a tilt of 1, so the power spectrum scales as k to the power of 1. And actually this is very close to what we observe today. It is not exactly the same, but it is just by simple arguments actually a power spectrum that is not far from what we see today. Okay, but this is without inflation. Now, problems that exist in cosmology before you know about inflation. Here's a diagram. This is our past light cone, and in fact, in the previous lectures I just put cosmic time here. That's not entirely fair, because this radius r is not a physical distance, it's a cone-moving distance. So r is not equal to c times t, but it is equal to tau in this case, which is a conformal time. So we have the homogeneous metric, scale factor times the spatial coordinates. And of course you can put the scale factor outside of the parentheses and redefine your time coordinate as tau with a squared d tau squared is equal to dt squared. It's a simple differential equation. You get a new time parameter. In these coordinates, the photon light cone the photon trajectory given by the s squared is equal to 0, then corresponds to d tau is equal to dr. So in plotting conformal time, we have spatial coordinates horizontally and time coordinate vertically. In conformal time, the photons travel on lines of 45 degrees in this diagram. I already argued by words that there is a maximum distance which we can span with our observations. We can only look as far back as the Big Bang. So, unfortunately the universe was opaque after the Big Bang and only became transparent at a later time. So, if you draw a horizontal line here, that would correspond to the time of CMB decoupling. That is when the universe becomes transparent. So we only actually can look as far back as the cosmic microwave background. So fundamentally our horizon extends all the way back to the Big Bang, and that is a finite distance. We cannot see infinitely far. If you lived at the epoch of CMB decoupling, so you live here, and all the light that you receive travels on lines of 45 degrees as well, the maximum distance that you can see is a smaller finite distance, simply because the universe is younger. So this is the time of CMB decoupling. So from this diagram you can already see that we span a larger distance with our horizon than observers who live at the CMB time. But moreover, we see two points in the universe, when we look at the CMB, or we see actually many more points in the universe, that cannot know about each other, because their past horizons do not overlap, so they have no single bit of information that can be the same. So they cannot be correlated. So in words, if you had radiation domination since the Big Bang, we don't know about inflation, and the CMB decouples at of the order 100,000 years after the Big Bang, then you can compute what the particle horizon was at the time of decoupling. We can compute at what temperature the photons decouple, given the constituents of the universe. And we observe the temperature today, so we know at which redshift it happens. So we have the physical size of the horizon orthogonal to our line of sight. We have the redshift at which it was. And then if you remember the definition of the angular diameter distance, which is the physical size at which you observe an object, divided by the angle at which you observe it, then you can compute what the angular scale would be of this hypothetical horizon at the time of decoupling. It's of the order of less than a degree. We see a cosmic microwave background with perturbations of much larger scales than a degree. And these perturbations are such that the most likely explanation is that it comes from a correlated field with correlations on scales larger than the angular scale of a few degree that we're looking at. Or even if you don't care about the actual correlations, just look at the temperature in each direction and the fact that it is only different by 1 in 10 to the 5th. How can it be that the CMB has the same temperature in every direction if these individual directions of the CMB at the last coupling, at the surface of last scattering, have never been in causal contact with each other? It should be affected by some random uncorrelated component. So the question then is, why is the cosmic microwave background so uniform? And this is simply the horizon problem. If the universe had been only dominated by radiation since the Big Bang, then the horizon size at the surface of last scattering is smaller than the size of the homogeneity that we observe in the cosmic microwave. And this is a puzzling question. There's another problem in cosmology if you don't have inflation, and that is the flatness problem. One ingredient in the metric that I have ignored so far is spatial curvature. If the universe is entirely homogeneous, and exactly homogeneous, then there's still the possibility that its topology is closed or open or flat. So it can be homogeneous, but a closed space-time, which means that if you freeze time and you look at a line infinitely extending into one direction, it will be a closed curve. It's like living on the Earth, it's a closed surface. If you walk in one direction, you end up at the same point again. And that equivalent in 3D. This is parameterized by this parameter kappa, which is the radius of the spatial curvature, of the spatial part of the homogeneous metric. Now, curvature affects the expansion rate of the universe. So, that means if you have no curvature, you get a different expansion rate than when you have a large curvature. Importantly, if curvature is large and positive, so you have a very close universe, the expansion rate will decrease all the time and will at some point go from positive to negative. So the expansion will become a collapse and the universe will collapse at some point in time. If kappa is equal to 1, this collapse will happen very soon and we will have never seen the light of day and we will never be able to observe the universe the way it is. So the curvature cannot be too large and closed. Inversely, if k is negative, the universe is openly curved, the expansion rate will converge to a very large constant value. Constant in the sense that a dot will be a constant in time. If curvature is very open and large, that means that the expansion rate will be very high. and there will never be any formation of structure because everything is being pulled apart so quickly that it cannot cluster and form the structures in which we live. So from the fact that we exist in a solar system that has the age it has, and that we observe structure in the universe with the abundance it has, we can already tell that the curvature cannot be too large. However, with ordinary matter, if we ignore the cosmological constant for a moment, we have here matter density and curvature, and the matter density scales depending on the equation of state of your matter, which can be 0 if it's dust, or 1/3 if it is radiation, or anything in between if it's an admixture of the two, which means that the density here scales as, if it's dust, it scales as 1 over scale factor cubed. Simply the density of particles decreases with the volume. If it's radiation, it scales as 1 over the scale factor to the 4th, which you can imagine as the density of photons decreasing with the volume, but the energy of the individual photons also decreasing with the stretching of the individual photons. That's where the extra factor of A comes from. If you fill that in here, you will find that the expansion rate, A dot over A, is always decreasing in time. So if you ignore the cosmological constant, then the second time derivative of A, given this equation, is always negative. Now if you look at the difference between matter and curvature in their role in the scale factor, then you will see that the contribution of matter to the scale factor, which in this slide call omega of t, is simply the matter term divided by the total of this equation, is 1 minus the curvature contribution, which is curvature over A dot squared. So the total matter contribution in an ordinary universe where A dot is always decreasing in time, or A dot over A is always decreasing in time, will be decreasing. That is, curvature always grows. The influence, the impact of curvature on the expansion rate always grows in time, if you have ordinary matter. We had the argument that the curvature cannot be too large today. Moreover, it's a growing function of time. So in the past, it must have been even smaller. Okay, it's a growing function in time, it cannot be too large. So when the universe was 1,000 times as small, the curvature had to be 1,000 times as small as well. The relative importance of curvature on the expansion rate had to be 1,000 times as small. So this is problematic. Why did the universe start out with that particular value of the curvature? Why did it have to be 0? 0 is an unstable point because it will always grow. Only the 0 value will be constant and always 0. The spatially flat universe will always remain spatially flat. But if it's slightly negative, it will always become more and more negative in time. If it's slightly positive, it will always become more and more positive in time. So why did it start so close to the unstable equilibrium value, and so close that it's still close to the unstable point today? This is the flatness problem. But you can see here already what the solution would be. The simplest solution is if A dot is growing in time. Because then the difference between the matter contribution to the expansion rate and the total expansion rate will tend to 1. Right, so in this slide it's very obvious to see how it's very clear to see what would solve the flatness problem. An accelerated expansion would. Okay. And that is what inflation is. Inflation to the rescue. Relating back to the horizon problem, here we have the same picture of distances as a function of redshift. In yellow we have the angular diameter distance. In red we have the co-moving distance, which is just a coordinate, it's a mathematical construct. And in blue we have the luminosity distance, which is the same as the angular diameter distance times a factor of 1 plus z squared. So the angular diameter distance relates angles of objects to their distance. Luminosity distance relates intensities of light sources to their distance. They're the same distance up to a factor of redshift squared. Now if we replace the expansion rate than we had previously with only ordinary matter by an expansion rate that at some point is a constant. If A dot over A is a constant, then A dot must be scaling exactly as A. So you have that A is the exponent, is some exponential of time. Bless you.
Thanks.
So if somewhere in the past the expansion rate became a constant, so A was accelerating in time, then the distances as a function of redshift will change, because remember that all these distances depend on the integral of redshift of 1 over h of z. If you replace it by a constant at some passing time, I think in this figure I did that here, very clearly see a feature, then the angular diameter distance doesn't anymore go exactly to 0, but it tends to a constant, it converges. So that means that even objects at infinite redshift will span a finite angle on our sky. Objects at infinite redshift will still be accessible by luminosity distance, but moreover, what happens to the horizon, the maximal coordinate distance at which we can observe? The co-moving distance to which we can observe tended to a constant, that's the horizon. But if you add an accelerated expansion in the past, the horizon actually becomes a growing function again. So if you go to z equal to infinity, this line tends to infinity. So this proves mathematically simply that an accelerated expansion changes the meaning of your horizon. And that means that if such an epoch existed, then the angular scale of the particle horizon at the surface of glass scattering is no longer a degree. It can be much larger than the entire. It can be much larger than the entire sky. It can be larger than 180 degrees. So if the accelerated expansion happened and it lasted for long enough, then the entire cosmic microwave background can already be inside its own particle horizon. Each point will have access to the same bit of information as each other point. And that is how inflation can help to cause correlations in the CMB and to make sure that the universe was in thermal equilibrium in parts that seemingly were out of causal contact with each other, because inflation brings them into causal contact with each other. Inflation makes the particle horizon potentially infinite. So, here we have the picture where the cosmic microwave background could not know from one part to the other about itself. Z1100 is the last scattering, Z0 is where we are today, Z infinity is the Big Bang. Now, if inflation happens, the amount of space-time between what we thought was the Big Bang and what's really the Big Bang can be inflated. That's where inflation comes from. It puts more and more space-time inside our light cone. Okay? I like this animation very much, so I'm going to show it again. You see? Inflation increases the past light cone in terms of redshift, pushes more space-time into our past light cone, and that means that these 2 points will have had access to the same bit of information. For this illustration resides here. The horizon problem is solved by inflation. The Big Bang is still at a redshift of infinity, but more space-time is pushed into our light cone. Okay? One way of phrasing it is that our universe stems from a much smaller patch of initial space-time because of inflation, blown up to big proportions by inflation, and hence it is causally connected. Alright? Are there questions so far? Only puzzled looks, but no questions. Very good. So, how would you get this type of inflation? How would you get accelerated expansion? And now I'm going to show you some Lagrangians. Some of you will appreciate that, because there have been so few equations before. This is an action of a theory that can drive inflation. Here we have the Ricci scalar, which is a function of the metric. So this is the Einstein-Hilbert term, which describes how space-time depends on the matter content. And here we have the matter content. In this case, we consider a single scalar field with a canonical kinetic term and a potential. The equation of motion for the scalar field is very straightforward. The difference with flat space-time is that here we have a term 3h times phi dot. And remember that h is the scale factor, gives the time derivative of the scale factor divided by the scale factor. So this term you can recognize as a friction term. So compared to flat space-time, the scalar field has the same equation of motion, except that there's an extra friction which comes from the expansion of space-time. Now let's first consider the homogeneous mode. For simplicity, we ignore spatial perturbations for the moment in the scalar field, and we look at how the scalar field evolves. So we have an object that is rolling down a potential with a friction that is given by the expansion rate. The stress-energy tensor is straightforward to compute. We have the kinetic terms here and the pressure there. So the energy density for the homogeneous mode is hence phi dot squared, the kinetic term plus the potential. The pressure is the kinetic term minus the potential. The expansion rate in this simple universe with only one scalar field is given by the energy density in the scalar field, the kinetic term plus the potential. However, the acceleration of the expansion, or the deceleration of the expansion, depending on the sign, is given by the energy density and the pressure of the field. So that is h squared times 1 minus epsilon, where epsilon is the ratio of pressure to density. So it depends on the equation of state plus 1. Which is, in this case, phi dot over h squared. And now notice that when epsilon is less than 1, the second time derivative of the scale factor will be larger than 0. So we have inflation. Or, in simpler terms, if you look at P over rho, the equation of state, it must be less than 1/3 if you want to have accelerated expansion. The simplest case is when it is exactly minus 1. That means that the kinetic energy of the scalar field can be completely ignored, and these two are given by simply the value of the potential. That means that the evolution of the scalar field is potential dominated, then P over rho is exactly minus 1. Now, if the potential is exactly flat, so there's no derivative in the potential, and the scalar field is lying still, then P over rho is exactly minus 1, and that is the case of a cosmological constant. If you don't have the kinetic term, you don't need the kinetic term, you just put a constant potential in the reaction, and you get accelerated expansion. So that's actually curious that I explained that today the universe is also expanding in an accelerated way. So, in fact, today we're also living in an epoch of inflation. So, we employ inflation in a very early universe to solve the flatness problem, and to solve the horizon problem, and to give rise to the perturbations, which I will explain in a moment. And it turns out that observations today dictate that today also the universe is expanding in an accelerated manner, and we're not employing it to solve a number of problems. It's just that the observations tell us that the expansion seems to be accelerated.
Yeah, but the first one is some acceleration.
It's at a different energy, yes.
Yeah,
That's what you said.
in a way, yeah.
Well, or what's the other difference that you mean?
I mean, in the past, when you, inflation, and you say it's accelerating.
Yeah.
But it's a huge acceleration.
Yeah, exactly.
Right.
Well, but energy scales just depends on how big your eyes are, right? If you can look at very small scales, you see large energies. If you look at very large scales, you see low energies. It is, but so it's true. It's at a completely different energy. But if there is some symmetry in the fundamental physics that we don't know, then you could imagine that there's actually some repetitive pattern in the history of the universe, and there are people working on theories like that. Nevertheless, I don't want to touch on that. I just wanted to point out that this is actually the same today and during inflation, and that is curious. That's all I want to point out. So, if epsilon is less than 1, we have accelerated expansion, because then P over rho is less than minus 1/3. Between minus 1/3 and minus 1. It could even be, you can perhaps write down a theory for which P over rho is even less than minus 1. But these models usually suffer many types of sicknesses. So you have ghost modes, etc. and everything diverges. So P over rho should normally be between minus 1 and minus 1/3 to get accelerated expansion. Now, I've written here P over rho, but we know what P over rho are, given the potential, so we can write down what epsilon is. And if you look at the homogeneous solution and you look at the first terms that you obtain, epsilon is actually related, so it is given by the time derivative of the scalar field divided by the expansion rate, but it is in fact related because of the differential equations for the evolution of the scalar field to the derivatives of the potential and the potential. So actually if the derivative of the potential relative to the potential is less than -1, if the blank mouse in there to get the dimensions right, then you also get accelerated expansion. There's a second term that will pop up in the later slides. That is simply if you add, if you look at the perturbations, you look at the evolution of the scalar field, the second order correction is related to the second derivative of the potential and the first derivative squared. I added here because it enters at the same order in the solutions that you write down as epsilon does. You need both epsilon and beta. So the only condition on epsilon is that it's less than -1 to get accelerated expansion. But if epsilon is much less than -1 and eta is also the absolute value of eta, because eta can be positive and negative, the absolute value of eta is also much less than -1, then you're actually in a regime that is called slow roll inflation, which is a convenient regime because there you can use perturbation theory and expand all your equations and get an analytical result for the perturbation equations and for the evolution of the scalar field. So this is just about the evolution of the background. You get accelerated expansion if you have a theory of a scalar field that satisfies the condition on epsilon that this is less than 1, or actually that this term is less than 1. And then you solve the horizon problem and the flatness problem. But now let's compute the perturbations in the scalar field, because inflation takes a region of space and blows it up to massive proportions. And if inflation goes on for long enough, you can infer that the scales that are on our visible sky today originate from a region that was close to the Planck scale at early times. And these are scales in which quantum mechanics, quantum field theory plays an important role. You can so actually, the scales that we see today come from a region in which there were quantum correlations. So let's compute what the perturbations look like. And in fact, I want to point out that all these perturbations will seed, the perturbations in the scalar field and the expansion rate itself will seed perturbations in the metric. So in the space-time. And I wanted to point out what are the different components in the metric that you can use for perturbations. Here we have a scalar term, here we have a term that can be decomposed into the gradient of a scalar and a pure vector, and here we have a term in the spatial part of the metric which contains a pure scalar term and a term that can be decomposed to scalar, vector and tensor terms. So not is the time component of the metric, this is the time-space component of the metric, and this is the spatial part of the metric. These are all the perturbations that you can get in general relativity: scalar, vectors and tensors. Now the scalar perturbations will be seeded by the perturbations of the scalar field. The tensor perturbations are interesting because because tensors are a propagating degree of freedom in gravity, tensor perturbations. That means that if gravity is quantizable and the metric can be treated as a dynamical object that satisfies certain commutation relations, then if you consider the vacuum, you will get quantum fluctuations in the tensor modes of the metric. You can write this all down, and you may ask, well, but why are we doing quantum gravity? Because I thought we didn't solve that. The point is that we're looking at the infrared part of quantum gravity. And if gravity is quantizable and it has some UV completion that works, then given the way we know quantum mechanics works at lower energies, it must look like canonical quantization for the tensor part. So actually this is for some people a well-kept secret of cosmology that we're actually doing quantum gravity quite regularly. But it's only the infrared part. We don't care about the UV. And Fortunately, the perturbations in the tensors look very much like the perturbations in the scalar field. So I will only treat one set of perturbation equations, that's actually the perturbations in the tensor field, and show you what it looks like. So, we have the tensor field decomposed in its 2 degrees of freedom, if you remember from your GR classes, the pluses and the crosses. They both have an amplitude that you can treat as if it were a scalar. But fundamentally, of course, we're talking about tensors. The scalar perturbation can be decomposed in Fourier space. These, at this point, are just amplitudes, phi of k and tau, and some normalization, b of k, times the Fourier mode, and here's the complex conjugate. Now let's write this amplitude in terms of a new variable u, which is the scalar factor, the scale factor times the scalar field. Then it satisfies this equation of motion, if you take the actual equations of motion that I showed previously. So we take the homogeneous part and we look at the first order perturbation in the scalar field. This is the equation of motion for the tensor perturbations. And for the scalar perturbations it looks very much like this, except that the Hubble term will have a slightly different shape. It's slightly different, and it's relevant that it's different, and I will explain why later. So this is, of course, a damped oscillator. That means that if you look at very large wave numbers, the ultraviolet limit of this equation, k squared dominates over the second time derivative of the scale factor. Note, by the way, that this is a second time derivative with respect to the conformal time tau. K dominates the ultraviolet limit, so there it is a harmonic oscillator with a simple solution. The other limit of this equation is k much smaller than the Hubble friction term. We're looking at scales that are much larger than the energy scale of the expansion rate of the universe. There the solution is also simple, namely u scales as the scale factor. But remember that u scales as the scale factor implies that the scalar field is constant. So if the perturbation of inflation in tensors tell you that for ultraviolet modes you get a harmonic oscillator, and for very large modes you get a constant as a result. Note that by the shape of this equation, actually you could divide out k and make it part of your time parameter. This solution really depends on k times tau, and you see that actually in equations. So, well, k here acts as a normalization as well, but the time dependence is the same as the scale dependence. So we've seen this in the previous lectures. This means that any mode that you consider walks through the same evolution, but at a different time. So let's look at a relatively small value of k, that means large scales today. There is an epoch in which k was much larger than a double prime over a, which means that there is an epoch in which this scale that we're considering was at a distance that is so small that it didn't yet notice so much the expansion rate. It was more subject to itself, and it acted as a harmonic oscillator, oscillating in time. This mode evolves, the expansion rate changes, and it will reach a point where it is much less than the expansion term in the equation, and it will go to a constant. So during inflation, every mode that is a harmonic oscillator at small scales is stretched by the accelerated expansion of space-time and stops oscillating. It freezes in. Okay? This is just the classical evolution of the classical evolution of generic perturbations in this field. I haven't said anything about quantum mechanics yet. Quantum mechanics give the initial conditions for this equation. So now let's turn these normalization factors into quantum operators. This is canonical quantization. Commutation relation is what you expect from your quantum mechanics courses. The canonical momenta of the field are given in the way that you used to the variation of the Lagrangian with respect to the time derivative of your field, which in this case we can give explicitly is the scale factor times the time derivative of the field. And then in canonical quantization, the commutation relation turns into this shape. The commutator of phi and the canonical momentum is again given by I times the Dirac delta function. If you plug in this shape, if you plug in the this solution, I went back one too far. If you plug this solution of this equation in the ultraviolet limit into this commutator relation, you get a normalization condition when your prefactors in the solution are U coming from this Wronski relation. So why can we do this? Because we're looking at a space-time that is expanding, and we're looking at gravity. Quantum mechanics should not be this simple. It's because, let me go back to the last slide one more time, it's because of the shape of this solution. Because look at this equation. For very early times, when the wave number is much smaller than the Hubble rate, much smaller than the acceleration of the expansion, this equation is a harmonic oscillator. And we know how a harmonic oscillator quantizes. This is the fundament of quantum theory. And that's actually a situation which we can probe in the laboratory, except that it's at different energy scales. But the harmonic oscillator in vacuum quantizes in a very well controlled way. So any mode that you consider during inflation has been in a state in the far past where it was on some small scales that the equations tell you that it was as if in vacuum. And that's a situation that we can quantize. So we then employ our machinery of canonical quantization, and we find the right normalization for our oscillatory solution that tells us exactly how this mode evolution works, what it looks like. And then we can make a long jump and skip the parts of relating that to the curvature of the universe. One reason I skip it is because...
Aren't you assuming that K is large enough?
Excuse me?
Aren't we assuming that K is large enough compared to...
How do we assure this? Is that your question?
Yeah, you are
Yeah.
put K
So-
much larger than
Yeah.
whatever
how
you
do
have,
we-
that's
yeah.
all you have. I mean.
Yeah. So during inflation, this function is, let's see, is growing in time.
Now I'm just worried about the ultraviolet versus the infrared part.
So if this function is growing in time for any mode k, if you go back far enough in time, this will be larger.
Mm-hmm.
So inflation must have lasted for some minimum duration in order for each mode that we can see to have been in that state. But does that answer your question? You're worried about the infrared and ultraviolet?
Yeah. Where are we? Are we trying to... I mean, I have thought that, you know, these perturbations are in the infrared limit.
I'm not sure if that is if that statement is really talking about the same perturbations.
Yeah, that's what I'm positive.
Yeah. So certainly the normalization of the quantum fluctuations.
Oh, now from there I understand. I mean, all what's written is fine.
Yeah. So but I'm not sure what this statement about the infrared limit refers to. So.
I mean, when you talked about the tensor part and that it's gravity, that we are...
Ah, yes. Yes, yes.
Right?
Yeah. Now I see your point. The statement about the...
Yeah, and that we're doing that, but you don't care about the ultraviolet part. Well,
yeah.
fine, very good.
Yeah.
But then...
But then we go to the ultraviolet and
Yeah,
normalization.
to...
Yeah. I don't know what the right answers are. I'm not a specialist in quantum.
Okay, never mind, it's all right.
In quantum gravity.
So I'm just to tell you I'm following.
Yeah. No, I'm happy that you're following. So I could come up with some words that may give you a more eased feeling about it, but they may not be correct. So I'd rather say that I just don't know. Okay. So the quantization gives us normalization of the scalar field. It gives us the expectation value for the amplitude in the scalar field. And it also gives the correlations in the scalar field. And these correlations evolve with the description given by this variable, this function u of k. So we have a correlation at a wave number k in our spatial, in the spatial distribution of our field. We have spatial correlations that come from quantum mechanics with a normalization given by canonical quantization. And now here comes the reason why I emphasize so much that we need an infinite number of universes to actually measure those correlations. If you do an experiment with quantum mechanics, for example, you make an electron fly past a double slit. If you do the measurement only once, you will see. If you do the measurement only once and after the double slit you measure the individual electron, you will only measure it in one position. But if you, of course, the quantum state of that electron is a correlated state, but by the measurement you collapse it into you make it collapse, and then you measure the individual electron somewhere, and then you no longer have the spatially extended correlated state. So if you can only measure individual electrons, and you cannot measure the coherent quantum state, you make it a classical state every time you measure. So then you need to do an infinite number of measurements to actually measure out what the original coherent state of the electron going through the double slit was. Does it make sense? So in cosmology, we only have access to a universe that is, because of its large size and the massive number of particles, is a classical system. The origin of the perturbations are coherent quantum states coming from the scalar field. But because of one process or the other, which I will not go into the details of very much, these coherent quantum states collapsed into a classical state, which means one answer to your measurement. No more quantum coherence. But the position of your energy perturbations, if you can measure infinitely many of them, will follow exactly the quantum coherence state. Okay? So if we want to probe the quantum origin of perturbations in the universe, ideally we would need to observe an infinite number of universes. Because you really want to observe, did the electron pass the slit here, or did it pass the slit here, and you have to do that infinitely many times. We have a large universe with many particles, so we do have many electrons passing through slits, but it's also many different slits. Right? So what we're doing implicitly, relating it to the double slit experiment of the electron, we're implicitly saying, well, here I have a double slit and the electron ended up there, here I have a double slit and the electron ended up there, here I have a double slit and the electron ended up there, and we put that all on one pie and say it was one single double slit, and we have the distribution function of the electrons passing through the double slit. That is what we're doing implicitly when we're taking the Fourier transform of the matter density field in the universe and saying that the power spectrum of that field measures the correlations laid down by inflation. But that's implicit. We don't observe that it is the case. If we had access to an infinite number of universes, we could, for each of the double slits that is out there, say, well, the electrons are distributed this and this way. Okay, so I described how the perturbations evolve in the scalar field and in the tensor fields. In the ultraviolet, there are harmonic oscillators, but due to the accelerated expansion of the universe, they reach a state in which they become constant in time and are no longer oscillating. This is the freezing in of the modes. But these are perturbations in some scalar field, and of course you need to relate that through the Einstein equations to the actual perturbations in the metric. If you write that down, you get the perturbations in the metric, and you can write down what the power spectrum of perturbations in the metric is. And this is interesting because what we observe in the universe is structure, which probes the gravitational potential. Remember that when we look at the cosmic microwave background, we're mostly observing the gravitational potential. There's a hotspot in the CMB where the gravitational potential had a high value. It's a hill. We observe a cold spot in the CMB where the gravitational potential had a low value. It's a trough. Because the photon had to climb out of a deep trough. That's why the power spectrum of curvature perturbations is the actual thing that we want to compute. And I will skip this term. It is related directly to the expansion rate during inflation, but divided by this thing epsilon, which I showed previously what it means. And it turns out that the answer is that your P of k is a power law, k to the power ns minus 1. And ns minus 1 through this relation is related to epsilon and eta. And that's why I showed epsilon and h briefly. So the power law that describes the perturbations in the scalar components of the metric is given by epsilon and eta. And I omitted to put epsilon and eta again on this slide, but let me repeat them quickly for you. This slide. Namely, there they are, epsilon and eta. Epsilon measures the first derivative of the potential relative to the potential. Eta measures the second derivative and the first derivative of the potential. And these two quantities measure really the derivatives of the scalar field, describe what perturbations in the scalar part of the metric look like. But importantly, the normalization of these perturbations, so this number 10 to the minus 5 in cosmic microwave background, depends on the scale vector on the expansion rate during inflation divided by epsilon. So we only know some ratio of derivatives with respect to the actual function. We don't know the normalization of the scale vector if we only know the scalar perturbations. So if we only measure the scalar perturbations, we don't know at which energy inflation happened. And the only bounds on the energy scale of inflation that we can put come from the arguments of solving the horizon problem and solving the flatness problem. And additionally, the argument that each mode that we observed once was in the ultraviolet state. The tensor perturbations, so remember that these are the perturbations in the spatial part of the metric, which are pure tensor modes. And these are not sourced by the scalar field, but these really come from a commutator relation on the metric itself. So these only exist if quantum gravity exists. The normalization of those is directly proportional to the expansion rate during inflation. And it's also a parallel with some tilde n. Happens to be that n is equal to minus 2 epsilon. Again, the derivative of the potential divided by the potential. And this is why it is, well, actually these are several reasons why the observation of tensors would be so extremely exciting. It has many consequences. It means that we can probe directly the energy scale at which inflation happened. And current theory tells us that this is at energy scales way above the energy scales that we can probe with particle physics on Earth. It's of the order of 10 to the 13th GeV. Actually, you may encounter 10 to the 13th and 10 to the 15th GeV in claims, but that is because in one case you're talking about the expansion rate, and in the other case you're talking about the value of the potential of the scalar field. But that's the typical value. Actually, the range of values is larger. And also importantly, remember that epsilon is strictly between 0 and 1 during inflation. So the tilde of the tensors is strictly smaller than 0 if they are produced by inflation. So, what does that mean? That means that inflation gives a prediction that is falsifiable. If we only have access to the scalar modes, there's not much we can do. We cannot even infer the energy scale of inflation. We can only tell what the shape of the potential was during inflation, relatively. I mean, that is already a big step because we have access to physics at very large energies. But it's really, really important to try to get access to the tensor modes generated during inflation. You're probing quantum gravity. If they're absent, then we will not know from that experiment if gravity is quantizable. If they're present, we know that gravity must be in one way or the other quantizable. If they're present, but they have a spectral shape that is larger than 0, that means tensor modes in the smaller scale, so the ultraviolet direction, have a larger amplitude than tensor modes in the infrared. That falsifies inflation, because that means that the tensor modes were generated with a scalar tilde, were generated with a tilde that is in the wrong direction. That falsifies inflation. So the funny thing is that your first reaction to observing tensors, like in the bicep measurements of last year, the possibility that they are there, is wow, they have observed tensors, that is the verification of inflation. But no, at the same time, there's the risk that tensors are actually the falsification of inflation if they are observed with a blue tilde.
I'm going to say something which is a bit stupid, but nonetheless. As soon as you say that there is Planck mass,
Planck mass, yeah.
haven't you assumed that there is an H bar there?
Yes.
Okay, so that implicitly assuming that, you know, gravity is quantizable, because otherwise I wouldn't put an H bar.
So it's
Because gravity, you know, is just the G and whatever you have.
yeah.
It's just the
Mhm.
William Tell constant
Yeah.
you have today. And, you know, then you just assume that there is some quantization, and then you move to X to K, and then you put the H bar. So implicitly, H bar is there.
Yeah. It is there. But if gravity is quantizable, then the low energy limit must reproduce physics.
All right, that's
And there you have H bar.
fine. But there, even in the scalar, there is an H bar.
Yeah. Yeah. No, that is true, and that is also why it is interesting to have access to both the scalar perturbations and the tensor perturbations, because then you will be able to tell whether the scalar field had to have values that probe a range larger than the Planck mass in energy ranges. I forgot to put a slide in showing that. Let me check. Yeah, no, I'm not showing that, so let me explain that here, because it is important to emphasize. Epsilon probes the derivative of the potential, and eta probes the second derivative of the potential. The tensors probe epsilon once more, so you can, if you have both tensors and the scalar tilt, you can cancel out the epsilon here, and you're left with the value of eta, so you know the second derivative of the potential. If you have the scalar tilt and you have the tensor tilt, you know the first derivative of the potential, the second derivative of the potential, and the absolute value, the scale of the potential of the scalar field. Now, if eta is positive, it means that you have a, well, I also forget the meaning of concave and convex, but we have a scalar field here, minus some fiducial value, and we have the potential of the scalar field here. If eta is positive, the second derivative is positive, so the derivative of the scalar field is growing, which is, for example, the case if you have m squared phi squared as your potential. Then, if you do some more algebra, and you want inflation to satisfy all the requirements that we have on it, for example, solving the flatness problem, solving the horizon problem, giving the perturbations that we observe in the scales that we see, then the difference in the value of the scalar field here and here, so we call this phi 1 and phi 2, the difference will be of the order of the Planck mass. But if eta is negative, then, so eta larger than 0, then we get this condition. If eta is negative, then we have the opposite shape of the potential. So we have eta less than 0, then we know that phi 2 minus phi 1 is much less than the order of the Planck mass. And now, that's another reason why last year's observations of bicep were exciting, because then they implied that the scale of inflation is of this type. Is it convex or concave?
I think it's convex.
Okay. It's a convex potential. And they would suggest that the scalar field has traversed values that span more than Planck mass. And that's curious, because we're employing physics that we know from Earth experiments and from theory that is at low energies. We're deploying it at energies that are way beyond the scale which we believe is the cutoff scale, fundamental cutoff scale for the theory that we're using. Could be correct, could be no problem. It could be that effectively, it could be that your effective description of physics remains the same at different energies, just with different fundamental ingredients that lead to this effective description. It could also mean that you're doing something that's just wrong. Okay, so now I've given you roughly what generates the spectrum of curvature perturbations and the spectrum of tensor perturbations during inflation. We have an accelerated expansion. We start with an harmonic oscillator in the ultraviolet. It gets stretched out. The oscillation stops. The mode freezes in, and we generate a correlated density perturbation on very large scales. So these scales are large for us today, but these two parts of space-time actually really come from the same ultraviolet part of space-time before inflation. So I showed you the slide with the Harrison-Sadovich and the best fit to with the Harrison-Sadovich spectrum and the best fit to observations, and the possibility of no two-point correlation functions. But now we actually have a mechanism that generates this spectrum of perturbations. We replace the arguments that just based on what we observe tell us what the spectrum must have been by a mechanism that generates the spectrum. Moreover, the mechanism that generates the spectrum predicts that the scalar tilt, so the power law according to which the power spectrum evolves here, is slightly less than 1. If you want inflation to predict the scalar tilt that is exactly 1, so exactly Harrison-Sadovich, you run into trouble, because then it would be impossible to end inflation, and it's actually difficult to probe what the normalization would be of the perturbations, etc. Inflation generically, for a standard potential that is not exactly flat, predicts perturbations in a spectrum that has a tilt just less than 1. And that is in absolute agreement with what we observe. So now I show the matter power spectrum here as a function of wave number, but we can do the same for scalar perturbations in the CMB and tensor perturbations in the CMB temperature. This is the prediction by theory from standard inflation for the temperature correlation in the cosmic microwave background. Correlations on scales that are much larger than what we believe is the horizon scale. Sorry, we don't believe it anymore. Correlations on scales that are much larger than the scales which we would believe to be the horizon size in terms of inflation. The horizon now, we believe, because of inflation, is much larger than the surface of mass scattering, than our surface of mass scattering. So here we have multiple moments CL as a function of multiple L, and these CL give us the power in the temperature perturbations, given by the scalar perturbations in this panel here. It turns out that the tensor perturbations also affect just the temperature that we observe in the cosmic microwave background, and they produce an additional spectrum of perturbations in the temperature that follows this shape. But I must point out to you the normalization of these axes. It's not clearly readable, but here it's times 10 to the third and times 10 to the fourth, 10 to the fourth, 10 to the fourth. Here it is all times 10 to the third. So this is a generic prediction of the tensor contribution to the temperature power spectrum. It's an order of magnitude lower than the scalar contribution to the temperature spectrum. Moreover, you could just change the tilt a little bit of the scalar to reproduce the contribution of tensors. That is saying that if we only have access to the temperature observations of the temperature correlations in the CMB, sorry, the temperature perturbations in the CMB, there's no way of telling whether they come from scalar perturbations or a sum of scalar and tensor perturbations. So observations of the CMB temperature itself cannot tell us what the scale of inflation was. They cannot tell us whether gravity is quantizable, and they can hence not tell us if the potential during inflation was convex or concave. Alright, and here in the bottom slide, in the bottom panels, there are the polarization spectra from scalars and tensors. They look very different, but also different by an order of magnitude. And I will talk in the next lecture about polarization of the CMB. So this is just an appetizer to hint at the fact that tensors may be observable in polarization. That's exactly what last year's excitement in the bicep announcement was. So, what are the knowns and the unknowns about inflation? Scalar perturbations give away the derivative of the potential relative to the value of the potential, but they do not give away the exact value of the potential. They do not give away the scale of inflation. We would need an observation of the tensor perturbations to set to fix the scale of inflation, the energy scale at which it happened, to understand the physics that we're looking at. What is known is that the tensor spectrum, if it comes from a standard, simple inflationary theory, is strictly red. A blue tensor spectrum would absolutely falsify inflation. Okay? Of course, if you tell this to a theorist, he goes to his office and starts constructing a model that does give you a blue tensor tilt inflation. There are papers around that claim that you can get blue tensors with very particular models of inflation. I have not studied them, so this statement is only true for a generic class of models, but it may not be true for any fundamental theory that produces inflation. But it would be a big downer for inflationists if the tensor tilt could be observed to be blue. So what I have not talked about, and what I will not talk about, because this is the last slide, is the possibility of multi-field inflation. I've only discussed a single scalar field rolling down its potential, but there's no reason for the scalar field to be alone. So there's a lot of activity going on in the inflation community, investigating the possibility of having multiple fields present during inflation at these high energies. And what interesting features that you get there, for example, is that inflation is rolling down the potential, but the potential has more dimensions because you have multiple fields, and it could be turns in the potential. So the inflation is not just rolling down a hill, it's rolling down a gutter, and there can be turns in the gutter in your two-dimensional potential or multi-dimensional potential. And these turns then would lead to interesting features that may be observable in the CMB, that may falsify other models of inflation, etc. So there's a lot of possibilities. There's a lot of possibilities in this field, the field of multi-field inflation. Another thing that I have not talked about is the fact that this single scalar field produces a spectrum of perturbations that is practically Gaussian. I say practically because only at the linear level it will be absolutely Gaussian, because we're talking about an individual degree of freedom doesn't couple to anything. But if you start computing second order perturbations in the scalar field, you do get corrections, and since it's second order, it's non-linear, so you expect things that are non-Gaussian. Observations tell us that the perturbations in the temperature of the cosmic microwave background are Gaussian up to 1 in 10 to the 9th. So 10 in 10 to the 10th. But we haven't yet pushed that number down to 0, or to the value that is predicted by single scalar field inflation. More generic theories of inflation with multiple fields, if they are coupled to each other, etc., do produce non-Gaussian features in the cosmic microwave background. So the absence of non-Gaussianities already rules out certain classes of inflationary models, but the constraints are not tight enough to rule out all multi-field inflation models. But I haven't talked about it, and I think I will not talk about it so much in the other lecture. So, what's up next week is the polarization of the cosmic microwave background, and I will see if I can put in some other themes of cosmology as well, and maybe you have requests of something that I have not addressed in these 4 lectures and you want to hear about next lecture, so please tell me if you want to hear something. So that's all I wanted to say today. Thank you. So, are there questions?
I'll start by the last slide. Just for the moment, so the standard scalar field with slow roll really works well. Explain everything.
Yeah.
And so people are anyway trying to do something more complicated.
It's like a paracetamol, it solves everything. So, yeah.
But people are still trying to complicate the theory.
Yes.
Not to explain something, but just to prove that it can be fast.
Right.
Yes.
Right.
Okay.
Yeah.
So, I mean,
Well, I have an opinion about that, but it will be put on YouTube, so I won't tell you.
Just to be sure. Could you tell us again a bit more about why this PT would imply, so if we measure tensor mode, it would imply that we can quantify gravity? Because just from the equation, I cannot really see the difference. From the PT and PR that you show us.
It's simply the fact that you have APT. It's simply the fact that you have perturbations that come from tensors at these large
Because
scales.
they are produced by the inflation, and so I don't see really the link with the quantum gravity. So.
They are not produced during inflation if gravity is not quantizable. Because with the commutation relation that I wrote down, this commutator, okay, by the notation I use, it is perhaps a bit misleading because I write down the phi. But actually, the equation of motions that I've written down are for the 2 degrees of freedom of the tensor fields. So this phi is not a scalar field, it's the amplitude of the tensors. That means that this commutation relation is really a commutator in degrees of freedom of the tensors. It's really a commutator in gravity. You don't need inflation for this commutation relation. But you need inflation for these perturbations to be stretched to scales that we can observe.
Okay.
Right? So this commutator is in the gravitational fields, in the tensors. So if we observe P of t, then we know that this commutator is non-zero. So we know that gravity must be quantizable.
Okay. And I don't get this argument because phi 2 and phi 1 are still the same in your drawing.
Well, I didn't give scales to them.
Okay. But it changes when you win.
Yeah.
Actually, it changes when you change the eta.
Yeah, exactly. So, so actually, what I should be drawing here is this divided by phi 2 minus phi 1, make this phi 1. And then this goes from 0 to 1, right? That's what I should have drawn.
Okay.
Good. More questions? I'm only looking at you for questions.
Yeah, the last one, because you said for inflation, we know that the tilt should be just less than 1.
Yeah.
The scalar tilt.
Scalar tilt would be just less than 1. And the
I
tangent
know.
tilt would
So
be just...
the tilt, it's this k to a power ns minus 1. So it means that ns minus 1 should be just less than 1.
Just less than 0.
Just less than 0.
ns
should be less than
ns should be just less than 1.
Okay. And because I was knowing that ns is about 96 or something.
Yeah, exactly. That ns is, we put it, this ns is just less than 1, so this entire sum is just less than 0. Yeah. No, thanks for pointing that out. No more questions? Then are there any requests for the next lectures? Last lecture, I can discuss other topics in cosmology that I have no problems to discuss. If there's anything that you'd like to get explained or have discussed. No?
Some more polarization of the scene.
Yeah. Polarization of the CB is your request? Okay, so I have sufficiently at least you can see your brains with your desire to see polarization. Okay, well, then that's it for today. Thanks a lot for being here again. Thank you for sitting through all this with me.